All right, so in this presentation, we're going to talk about our second lecture from Chapter 8, dealing with time value of money, specifically talking about equal multiple payments. All right, so we're going to start dealing with cash flows that are uniform and predictable in nature, either in the form of perpetuities, which means payments that continue into infinity, or annuities, which are uniform payments with a finite end. So a perpetuity is a series of uniform discrete payments or receipts that continue forever or into infinity. In other words, perpetually. Now, an annuity also consists of uniform discrete payments or receipts that continue forever, but these do not. These payments come to a finite end, whereas perpetuity does not. There are two types of perpetuities, both with payments extending into infinity. There's a constant perpetuity, which consists of fixed uniform payments, and a growing perpetuity, which has payments that grow at a fixed rate. The present value for a growing perpetuity is the starting point for calculating the present value of a constant perpetuity. So you see now on the screen the formula for the present value of a growing perpetuity, or in other words, what would its price be today if I could value those cash flows? So what you do is you take your payment you receive, and you multiply it by 1 plus the growth rate, and then you divide that by the growth rate, G minus 1. And note that the interest rates and the growth rates here have to be in decimal form or percentage form, meaning out of 100, okay? So if we just had a constant perpetuity where the payments were always the same, G would equal 0, which would then yield a formula. The present value of a perpetuity would then be equal to the payment divided by I, once you do the algebra and simplify that, once you substitute G equals 0, okay? So now turning to an annuity. So an annuity consists of fixed regular payments into the future for a finite period of time. Note that perpetuities have payments that don't come to an end but continue forever, okay? There are many examples of annuities, such things as a lottery payout that we have here in the state of Tennessee. This consists of uniform annual payouts for a specified period of time. That's a common annuity. If you have a loan on your house, that's a mortgage, and mortgage loans are used to fund a home purchase that are paid back through uniform monthly installment payments, typically for 30 years. Yours truly would recommend 15 years based on our previous discussion from the last lecture. But these are also annuities. U.S. Treasury bonds are U.S. government debt obligations that promise to pay a fixed bond coupon payment for as long as the bond is outstanding. And these fixed coupon payments are also annuities, those interest payments. So an ordinary annuity is one where the payments are made at the end of the period, whereas an annuity due is one where the payments are made at the beginning of the period. And basically the difference in the timing here is an additional period of compound interest or an interest payment. So an example of an ordinary annuity would be interest payments on loans that are due at the end of the borrowing period, whereas an example of an annuity due would be a rental contract that requires rent be paid at the beginning of the month. Also, leases tend to also be annuities due as well. So to calculate the present value of an ordinary annuity and annuity due, we're going to use the following formulas that you now see on the screen. So let PYMT stand for payment, let R stand for the interest rate, and N stand for the number of periods. The present value of an ordinary annuity, PVA, is equal to payment times, and then we have a lot of parentheses and brackets here, but you see this, this is otherwise known as the present value interest factor of an annuity. So a lot of times accountants will just pull this number from a table, but from a business or finance perspective, you can actually calculate it. So to calculate it, it's going to be 1 minus and then 1 over 1 plus R raised to the n power, and then all of that is divided by R. The present value of an annuity due, the difference with that formula and the ordinary annuity formula is at the very end, you multiply it by 1 plus R. So that's an additional compounding period or interest period. Note that the above formula is an adaptation of the present value formula for an ordinary annuity, but with one more compounding period added. So a couple of notes here with regards to this. So, make sure that you understand what an annuity is, and then be able to apply what we learned from the last lecture into these things as well. So I would suggest that you do a couple of things. First, you should create a cash flow diagram that shows the magnitude and sequence of the cash flow spaced out over time. You should also create a table that identifies the independent variables and the dependent variable, meaning the thing you're solving for. So in other words, when you're given a problem, write out all your data and also do that in a timeline. Figure out what you're trying to solve for, what context or type of situation you're in, and then go from there. So our annuity time value money problems involve future value, present value, the number of periods, the interest rate, and the payment. Usually you're going to be given 3 of these or 4 of these, and you have to solve for one unknown. So, sometimes you might be solving for the present value if you're given the interest rate, number of periods, and payment. Other times you might need to solve for another variable like the number of periods once you're given a present value and payment. Note that the table approach I just described is particularly helpful if you're using a financial calculator, or more specifically, hopefully you're using Excel, as these inputs that feed both require that the known variables be inputted first, leaving the unknown variable to be solved for by the calculator or the software function. So some examples of annuities include lotteries and structured settlements that make a fixed periodic payout for a finite period of time. You can trade these series of fixed payments for a lump sum payment by solving for the annuity's present value, given the following function, where the present value of the annuity is equal to the payment multiplied by, bracket, 1 minus 1 over 1 plus r to the n, all divided by r. The other thing you could do is do 1 minus 1 plus r raised to the negative n power and divide by r. So whichever one you feel more comfortable with. Okay. So in these cases, an alternative is often presented to the recipient that allows them to convert the annuity into a single lump sum up front. So how would you determine if the lump sum is adequate compensation in exchange for giving up the annuity? So as an example, if you win the lottery, not that you should play the lottery, but if you were to win the lottery, typically you're given 2 choices. You either can take an annuity or you take a lump sum payment. Now, all of this is going to depend on what your assumed discount rates are, or in other words, what is an acceptable rate of return for you? So what you would need to do in these situations is solve for the annuity's present value, given your annuity payment, the number of periods, and the rate of return that the recipient requires on their investments. Okay. Another example would be you want to retire and you have to draw down savings to fund your expenses. This essentially is a matter of converting a lump sum into an annuity. So for example, if you have $1 million and you expect to live for another 30 years, you have an investment rate of 5%, how much can you expect monthly income from withdrawals from this fund? So solve for the payment, given that the present value is $1 million, the number of periods are 30, and the interest rate is 5%. Once you do the math, regardless if you want to do it by hand, or you want to use a financial calculator, or you want to use Excel, you should get $5,368.22 per month. Note that at this particular period in time, that is going to be much more than you would receive or withdraw from Social Security. Okay. So it's very important to save for retirement. Now, loans come in different forms. So here are 4 listed on the slide here. So term loans mean that you borrow a sum of money with a promise to pay it back after a certain number of years with a given interest rate. Revolving lines of credit means that funds can be tapped on as needed basis to fund gaps in cash flow needs, and you have to pay interest on the portion that you use. Personal lines of credit are loans made to individuals that, similar to revolving lines of credit, can be tapped to fund temporary cash flow shortfalls. These loans are either secured. For an example, you have to have like something underlying it, whether it be like a car or a lot of times home, like your house would be a home equity loan. Or it could be unsecured, like a credit card. Okay. Installment loans are loans that are paid back over time by periodic payments. Amortization means that you have an amount of money that you create an equivalency between the present value of the amount and periodic installments. So in other words, what's going to happen, you're going to solve for an annuity payment given your loan amount, the number of periods, and the interest rate. Or you're trying to solve for PMT given PV, N, and R respectively. So practice this example. Suppose you take out a $300,000 mortgage for 30 years payable in monthly installments at 3% interest. If this were to occur, you would solve for PMT, given that the present value is 300,000. N is going to be 30 years times 12 months in a year is 360, and the interest rate is going to be 0.03 divided by 12. Recall why we do this from the previous lecture. Okay, we're not compounding annually, but we're compounding monthly. So when we do that, we need to make the appropriate adjustments to the number of periods and the interest rate. To do that, we multiply and divide respectively. Once you compute this, you should get $1,264.81 per month. Below, you see something called an amortization schedule. This shows how an installment loan is amortized over time. So for example, suppose you take out a $10,000 loan that you're going to pay back annually for the next 5 years at 5% interest. You determine to pay the $10,000 off plus the interest, you will need $2,309.75. To confirm that this is correct, you can use the amortization schedule demonstrated below. In the first year, your beginning balance is $10,000. You pay $2,309.75. Since it's 5% annual interest, 5% of 10,000 is 500. Therefore, meaning that the principal you actually pay off on the loan is the difference between the annual payment and interest. So $2,309.75 minus $500 will yield $1,809.75. We subtract the principal from the beginning balance to get the new balance or the ending balance for the year at $8,190.25. Now for year 2, we take the ending balance from year 1 and carry it over to the beginning balance in year 2. We again make an annual payment. The interest is going to be 5% of $8,190.25, which is $409.51. We subtract the interest from the annual payment to give us the principal paid off on the loan of $1,900.24, giving us an ending balance of $6,290.01. We carry this balance over to year 3. We again make an annual payment of $2,309.75. The interest in year 3 is 5% or 0.05 multiplied by $6,290.01, giving us $314.50 interest. That's how much interest we owe. But we pay $2,309.75. So we reduce the principal amount by the difference in the annual payment and interest, giving us $1,995.25. This is how much we reduce the beginning balance by. So $6,290.01 minus $1,995.25 gives us an ending balance of $4,294.76. We carry this over to year 4. And again, we make another annual payment. And the interest now for this year 4 is 0.05 times $4,294.76, giving us $214.74. Once we pay the interest, the remainder goes to paying off the principal. So that principal amount is $2,095.01. We reduce the beginning balance by this amount, giving us an ending balance of $2,199.75. The interest in the final year is 0.05 times $2,199.75, giving us $109.99. If we add in this last year the beginning balance plus the interest, that will give us the amount of the annual payment. And that annual payment is used to pay the interest as well as the principal, which turns out to also be equal to the beginning balance. So now the ending balance is 0, meaning that we have paid off the loan. So the future value of any loan hopefully will be 0, meaning that we have paid it off. So anytime we're given loan details such as the loan amount, and the installment payments and term of the loan, we can determine the rate of interest or the cost of borrowing that is being paid on the loan. So in this case, we'll solve for R, or the interest rate, given the present value, payment, and N. which in turn are the loan amount, periodic installment payments, and number of periods, respectively. So suppose you borrow $1,000 for 5 years and make an annual installment payment of $238. Your cost of borrowing would be the present value is $1,000. N is the number of periods, which is 5 years in this case. And now the payment's $236 annually. So solving for R would give you 5.78%. That's your interest rate on the loan. When loans are stated in monthly terms, it is tempting to simply take the loan rate and multiply it by 12 to arrive at an annual interest rate. However, this is incorrect. Multiplying by 12 will yield the stated annual loan rate, but that stated rate will be different from the effective interest rate when compounding is taken into account. The formula for calculating the effective annual rate is 1 plus R divided by N, and then this number is raised to the N power, and then we subtract 1 on the outside. N is the number of periods and R is interest rate. So for example, a stated rate of 1.5% monthly for a year is equal to 1.5% times 12, or 18%. However, the effective annual rate, once we plug in 0.015 for R and N, let N be equal to 12, solving for this would give you 19.6%. Note that in banking and marketing, as well as finance and business world, usually what will happen is if someone's trying to get you to borrow money from them, they will quote you 18%, versus if they're trying to get you to invest with them, they will quote to you 19.6%. So be aware of the interest rates that are told to you as well as how they're compounded. So in assessing the cost of borrowing, the effective interest rate is the rate that matters to borrowers. Okay. Firms need to know their all-in cost of borrowing, meaning factoring in all related costs of borrowing. If you know this, this allows you to make better informed decisions regarding how to minimize cost. A firm's cost of borrowing factors into its weighted average cost of capital. So in this, now turning to 8.5, where we take equal payments, we can solve for the present value of a perpetuity using a financial calculator or Excel, and that involves the simple application of the perpetuity formulas we reviewed earlier. A growing perpetuity is the present value of that is equal to the payment multiplied by 1 plus G divided by G plus 1. If the perpetuity is constant, the present value will be equal to C divided by R sub S minus G, where C is the constant dividend rate, R sub S is the required rate of return, and G is the growth rate. Note again that PMT stands for payment. So if we want to use a financial calculator, which you don't have to, but if you do, you have PMT, PV, FV, N, and I buttons, respectively. Note, I strongly recommend you set up a table that identifies the independent variables and the one dependent variable, meaning the one you're solving for. Enter the known independent variables first, leaving the unknown variable until the end, and then the financial calculator will solve for the last variable as the unknown variable. As an example, if you're using a BA2 Plus calculator, you will punch in all of those variables, and then to find the last one, you usually will hit the CPT key, and then whichever key that you're searching for to find the answer, and the solution will be provided to you. If you're using Excel, you can use the PMT function to solve for payment. You can use the PV function to solve for present value. You can use the FV function to solve for future value. You can use the NPER or NPER function to solve for the number of periods. And to find the interest rate, you'll use the rate function in Excel. Make sure that you put in the arguments in the appropriate order. And if you don't need or don't have some of that information, make sure you just put an additional comma into that space or a 0. Note, some arguments are optional, so you don't necessarily have to include them, but just be mindful of what you're actually putting into Excel. So there you now see on the screen the Excel functions and how you solve for them. The future value, you put in the interest rate first, then the payment, and then the present value and the type is necessary. PV does the same thing except FV is swapped out for PV. The NPER function is solving for the number of periods. Use the rate, put the interest rate in first, followed by the payment, then the present value, and then the future value if necessary, as well as change the type. And then note that the interest rate function is interesting because at the very end, you can put in an optional guess. I would not recommend you do this for this particular class. So note that there is a difference again between stated interest rates and effective interest rates. So you can see that here on the screen. If you have an 18% rate, if it's compounded monthly, it results in an EAR or an effective annual rate of 19.6% using that formula there. And this again is just another example with the amortization table. Okay. So thanks for watching this lecture. The next lecture in Chapter 9 will wrap up our conversation with regards to time value of money, specifically looking at what happens if cash flows are not always the same. Thanks for watching, and I hope to see you in the next one.